Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, I am Sahib Noor and welcome to a new lecture of Physics 2. This is our lecture number 8 of the course, and in this lecture we will cover the remaining topic of chapter number 18 of our textbook. The title name of the chapter is Heat, Temperature and First Law of Thermodynamics. In this lecture we will cover topics related with the heat and Warden, and then we will discuss the first law of thermodynamics, and at the last part of this lecture we will discuss the application of first law of thermodynamics. So let's start our first topic of the lecture, which is related with the heat and Warden. In previous lecture we have discussed that heat is a type of energy which is related with the temperature difference of the object, and we have studied that heat is considered as positive when heat is added to the system, and heat is considered as negative when heat is taken from the system. Similarly, in this slide we will discuss that Warden by and on the system. Consider a system, a cylindrical system, which is placed on a heating reservoir. A reservoir is a hard plate whose temperature T can be controlled by turning a knob. In the adjacent figure we have a cylindrical system in which we take some points which represent the system elements, or it can be gas, and the points represent the molecule of the gas, and this knob can control the temperature of our system, and the slide is represented as the thermal reservoir. The wall of the cylinder are made of insulating material that does not allow any transfer of energy as a heat. The procedure by which you change the systems from its initial state to its final state is called thermodynamics, and during this process the energy may be transferred into the system from the thermal reservoir, which is called positive heat, or vice versa. Also, work can be done by the system to raise the loaded piston or lower it. So if this piston is raised, then the work is done by the system, and if this piston is lowered, then we can say that the work is done on the system. And some state variables are representing our system, and the state variables are P, V and T, where I represent the initial state of the system. So P represents the initial pressure of the system, I is the initial volume, and Ti represent the initial temperature of the system. When heat is added or taken from the system, then the state of the system will change, and we will represent it by final state PF, VF and TF. So consider a system in which we take a gas which push the piston through a displacement ds by exerting a force which is equal to PA. P represents pressure and A is the area of the piston. So the work done is given by work is the dot product of force and displacement. So the small amount of work which has been done by or on the system is represented by dW is equal to F dot ds. By putting the value of F, which is PA, pressure time area, and ds, we will obtain that area which is multiplied with the displacement. So we have a three-dimensional element which is the volume. So del W is equal to P dV. To find the total work done, we will integrate the equation, and W will equal to integral from initial state to the final state, or Vi, in which the volume of the system changed from Vi to Vf can be written as product of P dV. In this slide, we will discuss work done from a PV diagram. And when the volume change, the pressure and the temperature of the gas may also change. There are actually many ways to take the gas from state I to state F. For example, the work has been done while decreasing the pressure, so the volume of the gas will increase, and the work has been done, and the work has been represented by the shaded area in the adjacent figure. So when the pressure of the system decrease, this line shows that the pressure decreased while the volume of the system increased. So the work is done by the system, the piston will move up, and we consider that W is greater than 0. We have another way to do work done in two steps. In first step, we will consider that the pressure of the system is constant, and in second part of this work done, we take the volume of the system as a constant. In step 1, when the pressure is constant, the volume will change from initial state Vi to final volume Vf by changing the temperature using the knob. When we increase the temperature of the system while the pressure is kept constant, the volume will change from Vi to Vf, and the piston will move up. So the work has been done in this part when the pressure is constant, and this can be easily seen from the figure that our system is at initial state I, and when we keep the pressure constant, this line shows that the pressure is constant while the volume is changing from Vi to Vf. So when the volume change, the pressure constant, the work has been done, and this work is represented by W, which is greater than 0. In second step of this process, the volume is kept from A to F. The volume of the object do not change while the pressure is reducing, and the temperature is transferred to the reservoir. In this case, from A to F, the work is equal to 0, that is, the work is neither done by the system nor on the system. So the overall work done is taken to be positive, because when the pressure is constant, the volume is changed, so the work in that case is positive, is the work is done by the system on the environment. Now we will discuss the work done on the system. For this, we consider that some external force is applied on a system, and the gas will compressed, so its volume will reduce, and the work done can be represented on a PV diagram as. Consider the system is some initial state F, and when the pressure is exerted on the system, the volume will reduce, and the work has been done on the system. So W is taken as a negative, and this shaded area represents the negative work done, or the work done on the system. And there is a process known as the thermodynamic cycle, in which the system moves from some initial state to some final state and back to initial state. Such a cycle is known as thermodynamic cycle, and both type of work has been done in the thermodynamic cycle. That is, positive work done and the negative work has also been done in the same cycle, and this is represented by the adjacent figure, in which the system moves from some initial state to some final state and then back to initial state. This shaded area represents the work done, and the net work done is to be positive because the area under the thermodynamic expansion is greater than the area under the thermodynamic compression. The second topic of our lecture is to study the first law of thermodynamics, in which we study a quantity which will remain the same for all thermodynamic process, which is delta E, the change in the internal energy. As in previous topic, we have seen that when a system changes from a given initial state to a given final state, both the work done W and the heat Q depends on the nature of the process. If heat is added to the system, then Q will be taken as positive, and if heat is taken from the system, then Q will be considered as negative. And if the work is done by the system, then that work done will be considered as positive, and if the work is done on the system, then that work will be negative. Experimentally, it has been observed that all combination of Q and W depends on the path. Only Q and W also depend upon the path, as we have discussed earlier that Q can be negative and positive so as the work done, and similarly this combination or any combination of Q and W, for example Q plus W or Q minus 2W, etc., will depends upon the path. The only quantity which is left which do not change in the thermodynamic process or which is independent on the path is Q minus W, and this quantity is the change in the internal energy of the system. Delta E is equal to EF minus EI, that is change in the internal energy. I and T represent the internal energy, which is equal to the energy of the system at some final state minus the internal energy of the system at some initial state. If the thermodynamic system undergoes only the differential change, we can write the first law is dE, which represent the differential form of the internal energy, is equal to dQ minus dW, as the internal energy of the system tend to increase if energy Q is added to the system and tend to decrease if the energy is lost as work done by the system. The last topic of our lecture is to study the application of first law of thermodynamics. So in this slide we will discuss a process known as the adiabatic process, in which energy cannot be added nor subtracted from the system. So in this case the energy transfer as a heat is equal to 0, so Q is equal to 0, and when we apply the first law of thermodynamics to this process, in which the change in internal energy is equal to change in the heat of the system minus the work done, as Q is equal to 0, then we were left only with the internal energy, which is equal to minus W. So if the work is done by the system, the work is considered to be positive, and the internal energy of the system in this case will be equal to negative. And if the work is done on the system, so the W will be negative, and that negative will multiply with this negative, so the internal energy of the system will be positive. So a process in which the energy do not added nor leave the system is known as a adiabatic process, and the internal energy depends upon the work done. So if the work done is positive, the internal energy will be decreased, and if the work done is negative, then the internal energy of the system will increases. The second application of thermodynamics, in which we discuss a process with a constant volume, that is, the volume of the system do not change. So we will apply first law of thermodynamics and will discuss the outcome. So when the system volume is constant, so no work has been done on the system or by the system. So W will equal to 0, and when we apply first law of thermodynamics to a constant volume process, we will obtain that delta E is equal to delta Q minus delta W, as W is equal to 0. Then this implies that the change in the internal energy is equal to the amount of heat. So the outcome of this equation is, if Q is absorbed by the system, then the internal energy will increases. That is, when Q is added to the system, so Q is positive, and from the above equation the internal energy will be also positive. So this increases represent that the internal energy in this case is positive. And if Q is lost by the system, then the internal energy will decrease, as heat which is left from the system is considered as negative, and from this equation E is related with the Q. So if Q is negative, then internal energy will be negative, and this negative is represented here by the word decreases. In this slide, we will discuss the remaining two applications of first law of thermodynamics, that is the cyclic process and the free expansion. First, we will study the cyclic process. As previously we have studied that a process in which a body or a system moves from some initial state to some final state and then back to initial state, this process is known as a cyclic process. And if the system retains its initial state after exchanging the energy between Q and W, in this system the change in the internal energy is equal to 0. After applying the first law of thermodynamics to such a cyclic process, we will insert that dE, which represents the change in the internal energy, is equal to 0. So the W will equals to Q. Thus the work done during the process must exactly equal to the net amount of energy transferred as heat. The store of internal energy of the system remains unchanged. Another application of first law of thermodynamics is to discuss the free expansion. A free expansion differs from all other processes we have considered because it cannot be done slowly and in the controlled way. As a result, at any given instant during the sudden expansion, the gas is not in thermal equilibrium and its pressure is not uniform, and these are the free expansions are the adiabatic processes. And in adiabatic process, delta Q is equal to 0, and in the adiabatic process Q is equal to 0 as there is no change in the volume of the free expansion. So W is also equal to 0, This implies that the internal change in the internal energy will equal to zero when we apply the first law of thermodynamics to the system. So in free expansion, the change in internal energy is also equals to zero. So let's sum up our lecture number 8, what we have studied. In this lecture, we have discussed the heat and Warden. Heat can be defined as the energy which is flow from one body to another body due to the temperature difference. And we have also discussed the types of Warden, which is done by the system or on the system, and work is considered to be positive if the work is done by the system, and work is considered to be negative if the work is done on the system. We have also discussed the PV diagram, which represent the work done by or on the system. In the next part of the lecture, we have discussed the first law of thermodynamics, and we have studied that it is been experimentally observed that the quantity Q minus W for any thermodynamic process will not change. All other combination of Q and W cannot remain the same. Only Q minus W will be unchanged. And then at the last part of our lecture, we have discussed 4 applications of a first law of thermodynamics, in which we have studied an adiabatic process in which the energy cannot be added nor leave the system. That system is known as an adiabatic system. And then we have discussed an isochoric system in which the volume of the system is kept constant, and in that case the work done is equal to 0. And after this, we have also discussed the cyclic process and free expansion and applying the first law of thermodynamics, and have discussed the outcomes of these processes. In next lecture, we will discuss the electrostatic and the capacitance of parallel plate capacitor. So our next topic will be related to electric charge. And if you have any question or feel any difficulties, you can contact me at my email. Thanks and Allah.